Hi, I am Luis Quintero and I'm going to present the paper about the excitometer. Let's start with a brief introduction. Virtual reality has been used to effectively simulate real-life scenarios, and many researchers and clinicians have used virtual reality to study the psychological and physiological principles or to explore user perception and interaction. They commonly use self-reported measures like questionnaires or interviews, but they are not always reliable. In addition, if we want to provide personalized virtual reality experiences, we need data that can unveil all the unique and complex dynamics of the person. Therefore, we believe that bodily data can enhance virtual reality applications. First, because bodily data reflects the inner physical and mental states of a user, it can be recorded without interruptions during the interaction. It can be used complementary with self-reports, and it can support better the design of personalized experiences. Wearables are, of course, a reliable way to collect bodily data nowadays, very affordable and portable. However, there are some integration challenges, and it's that the software that is used to collect data from the wearable devices is not always compatible with the software, the game engines used to develop virtual reality experiences. In addition, you have raw physiological data in the way of time series that needs expert knowledge to be translated into usable information. And the third one is that this virtual reality data and the time series information from the physiology need to be annotated in such a way that they can facilitate post-session analysis. For this reason, we have created the excitometer. The excitometer is a software framework that allows developers, researchers, and hobbyists to integrate bodily signals in custom VR applications using the Unity game engine. The excitometer was designed based on the feedback of some potential end users that elicited a set of requirements using an online survey. There were 58 people answering the survey among researchers, developers, and clinicians, and they proposed that the main features for the tool should be to observe the user's physiology in real time, let the virtual reality application react according to the changes of a user, and to also analyze the user's reactions in an offline manner after they have interacted with the virtual reality application. This is a snapshot of the full architecture that we have implemented in the excitometer. The first blocks contain the data collection component where you translate the data from the wearable sensors into a protocol that's accepted by the game engine. We also have a module when we perform data logging and real-time feature extraction, where the raw physiological signals are translated into more meaningful metrics. And the last block is the integration that allows any virtual reality application developed in Unity to use these functionalities of physiological analysis. The first step is the data collection. We have made excitometer compatible with the Polar H10 chest strap, and we use the LSL protocol to communicate with the Unity game engine. There are applications available for Android devices or Windows, and you can see on the right side a snapshot of how the real-time data collection is conducted. The next step is an online UI manager where the Unity application will be enhanced with an UI that allows to analyze the data collection in real time, provide information about the sensor, and on the bottom left side you can add custom annotations according to what's happening to the virtual reality environment. Here you can see a sample of how the application is easily integrated in Unity. You just need to add some scenes, then start the devices for the data collections. Then you will see that in two panels that show the heart rate and RR interval. When a session has been finished, you have an online visualizer where you can explore the time series that were collected from the physiological sensors, as well as some metrics that are calculated internally in real time. Finally, when you drag the timeline, you can watch the images that correspond to this exact visualization or action that a user was taking while the signal was recorded. This allows post hoc analysis and user studies. We evaluated the excitometer in multiple ways. The first one was an analysis of the reliability of the data acquisition. We were not sure if embedding real-time data collection was going to affect the performance of the data samples. So we analyzed the data loss while acquiring with Unity and acquiring with a default LSL capturer, as well as we analyzed the errors in real-time feature extraction compared to an offline feature extraction. For the data loss, we found that there was no significant data loss when we were collecting data in Unity, as well as the features were validated as correct when compared to some Python packages. The second part of the system evaluation was a user study when we assessed the validity of the setup and the sensor. Recall that we are using the Polar H10 sensor, which is around 70 euros, and we wanted to know if this sensor can collect data as valid as the research grade sensor, the Live Amp, which costs around 20,000 euros. The results show that the lower correlation score between both sensors were around 0.947, which demonstrates and scientifically validates that the wearable portable devices can be used as an input for physiological analysis. Finally, we provide a use case example. Using the same setup than the last test, we took 4 360-degree videos from a common public database. Each of these videos has a specific score of arousal. Using the excitometer, we wanted to understand if there was a metric from the heart rate information that could correlate with the level of arousal of these 360 videos. In our small feasibility study, we demonstrated that a tentative metric of excitement level correlates with the level of arousal that is elicited by these 360 videos. This use case demonstrates an example of how the excitometer can be used for research purposes related with virtual reality and physiological signals. As a conclusion, we have shown the excitometer, which is an open source software tool to integrate heart rate activity in VR applications developed with Unity. The design was based on a survey which elicited the requirements among potential end users. The tool is easy to use and integrate by researchers, clinicians, and hobbyists without any experience in physiological analysis. The evaluation comprised data reliability, sensor validity, and a preliminary user study. In the future, we plan to embed analysis of motion trajectories together with the physiological signals. You can explore more on our website and access the GitHub repository. We want to provide some acknowledgments to the researchers and the institutions involved in this project. Thank you.